Good morning. My name is Jose Maldonado, and with me today is Dr. Susan Hendricks.
Hi, everyone.
Welcome to the latest installment of our continuing series of online courses. Today we will be presenting Confocal Stereology, a technical innovation from MBF Bioscience and ZEISS Microscopy. Before we continue, please take a moment to adjust your speaker volume so that you may listen to us at a comfortable level. We'll pause for a second to allow all of you time to do that. So, Sue, the very first question that we want to address here is, why would I want to perform confocal stereology? And the answer is simple. If you want to quantify spines, synapses, co-labeled cells, or other very small things such as fibers, you're going to want to have true systematic random sampling. You're going to want to have confocal X, Y, and Z stacks. You'll want to be able to rapidly delineate your region of interest at a low magnification to avoid photobleaching. And you're going to want the ability to automatically capture and place multiple confocal Z stacks at the correct X, Y, and Z positions relative to each other at high magnification within a single data file. Stereo Investigator, along with Zen software from ZEISS, work together for the efficient acquisition of confocal systematic random sampling image sites. A typical LSM stereology system configuration consists of a ZEISS 5 or 7 series laser scanning microscope running ZEISS Zen version 2009 or later. Additional components required are a motorized stage, a focus encoder, a digital camera with appropriate light source, as well as stage controller hardware. You'll also need a PC running ZEISS Zen 2009 or later, plus Stereo Investigator version 10.2 or later. In this webinar, you can expect to see a short introduction to stereology, confocal microscopy, and an explanation as to why the two are a natural fit. A step-by-step demonstration of Stereo Investigator along with ZEISS Zen for the acquisition and analysis of confocal systematic random sample image stacks. We will also have question periods throughout to allow you to submit your questions via the question window.
Any questions that are not addressed by the time that we finish this webinar will be sent via email to each participant.
So, Sue, in order to get started, why don't you take us through a brief description of what stereology is?
Sure, I'd be happy to. So stereology is an efficient means of quantification. It allows you to move from the qualitative differences that you may see to quantitative, statistically valid comparisons. It is considered the gold standard for reporting counts. Profile counting can be biased, and density measurements, the number of objects per unit volume, may not reflect the whole region or indicate a change in number. Stereology can be used to quantify a number of biological features, including cell population, cell size, regional volume, area fraction, or fiber length. The most commonly used stereological probes are listed on the right, and those are integrated into Stereo Investigator. We're going to focus on the optical fractionator probe, which allows you to quantify numbers of objects, so cell populations, synaptic numbers, spine numbers. In fact, Daniel Peterson pioneered the use of confocal stereology for quantifying objects using a confocal laser scanning microscope back in the 90s. And we've worked with him and since that time to continually improve the process to make it more and more integrated and intuitive. One of the hallmarks of stereology is systematic random sampling. What I mean by this is that we achieve systematic sampling to enhance efficiency by keeping the grid spacing and the counting frame size the same throughout all your sections through your region of interest. We don't want to count everything that's possible within your region of interest. We want to sample and only count a subset of the available synapses in the entire striatum, for example. It's randomized because the location of the grid, and therefore the counting frames, always starts at a random location. This is done by Stereo Investigator. And so to illustrate that process, if we were trying to calculate synapse number in the striatum, we would delineate the striatum, define our grid size and our counting frame size, and Stereo Investigator would systematically throw that grid with a random offset over the region of interest. With each successive throw of the grid, you can see that while the size and the spacing of the grid and the counting frame remain the same, the number of counting frames that overlie your region of interest and their placement is going to be randomized each time. Stereology also requires a thin depth of field. An important aspect of stereology is the ability to be able to discriminate whether or not an object interacts with your stereological probe. And so we need high resolution and a thin depth of field in order to be able to discriminate objects that are close to each other in X, Y, and Z positions. When you are performing stereology with bright field or wide field structured illumination applications, these thin depths of field are provided mainly by the objective lens, the numerical aperture of the objective lens. For bright field applications, it's also impacted by the condenser that's used. When you're looking for something that's very small, however, you want to be able to have greater resolution than can be provided by the objective alone.
That's right, Sue. And in situations where users try to perform stereology using wide field fluorescence, this can really become evident. Now, we've worked with ZEISS in the past to provide an integration with various types of their hardware. And what we found is that our users require more and more precision in X, Y, and Z to be able to identify their objects of interest. To this end, we've also integrated the use of structured illumination devices, such as the Apotome 1 and 2. The Apotome operates by removing out-of-focus light through an algorithmic process and the application of shadows onto your tissue. The differences can be quite remarkable. You could see here that a wide field image incorporates a lot of light that is above and below the focal plane of your region of interest, whereas a structured illumination device will give images that are much sharper in X, Y, and Z and allow the user to define objects of interest much more clearly. In regions of anatomy where cells are very densely packed, you can see the difference right away. The natural progression is to use Stereo Investigator to perform stereology using confocal microscopy. Confocal microscopy differs fundamentally from wide field and structured illumination in that it physically eliminates the light coming from below and above your focal point from ever entering the photodetector. This critical piece of hardware is known as the pinhole, and the diameter that you set your pinhole has a relationship to the optical section thickness. Using a high numerical aperture and a pinhole set to the airy disk unit of that combination of wavelength and numerical aperture of your objective will result in very thin depth of field images. Because a confocal images only one point in space at a time, it becomes necessary to scan that focal point in X, Y, and Z. Confocal image scans in X, Y, and Z result in confocal image stacks. As you can see here, with an LSM, it's possible to exclusively image a very thin optical slice out of a very thick biological specimen. Under suitable conditions, the Z dimension of such an optical slice can be less than 500 nanometers. As you can see in the image here, the same region of interest imaged in both wide field and with confocal yields vastly different results. It's clear that with a confocal image, it becomes much easier to see bright, tightly packed, small objects. The LSM-7 series from Carl Zeiss Microscopy is the hardware that we will be using throughout this demonstration. The class-leading image quality of a ZEISS LSM combined with the novel stereology software of MBF Bioscience provides researchers with an integrated, turnkey confocal stereology solution. The confocal microscopes from ZEISS are run with ZEISS Zen, or ZEISS Efficient Navigation Software. Zen is software that now comes with all Carl Zeiss confocal LSM systems. It's easy to operate and quick to learn. Zen provides control of all of the technical features of the LSM. we will be using Zen to set all of our imaging parameters for our SRS image stack acquisition, as well as to drive the laser scanning microscope. We believe that SI with Zen is the most tightly integrated and easy-to-use solution for confocal-based systematic random sampling stereology. Working together with these two pieces of software, users are taken through the process of acquiring image stack series from multi-channel stained tissue, which are then suitable for offline stereological analysis. Working within these two pieces of software, users are able to trace the region of interest, define the tissue thickness, define both imaging and stereological parameters, as well as execute the automated acquisition of SRS stacks. To give you a brief outline of what we will do next, Sue and I will be discussing the hardware configurations that are required to perform confocal-based stereology. We'll show you how we work with ZEISS Zen software as well as Stereo Investigator software to optimize the image parameters and then acquire the SRS image stacks. So Sue, before we continue, why don't you tell us a little bit about the hardware configurations that are required for doing this kind of stereology?
Sure. So if you are a current Stereo Investigator customer right now, you're very familiar with what's required in order to use your software efficiently. One of the hallmarks of it is calibrating your objectives to match the scaling for your acquisition device. In this case, it's usually a camera. Now that we're integrating with the ZEISS LSM confocal, we also need to define lenses for each of the laser lenses that you're going to be using. And that includes zoom and image size parameters as well. So if you have a 100x objective, you would calibrate a lens for that 100x objective, the 100x objective with a zoom of 5 and an image size of 512 by 512. It's as simple as that.
And so this is so that when images come from the LSM and the Zen software and it comes into Stereo Investigator, the two pieces of software can communicate as to the appropriate dimensions of the image, correct?
Yeah, that's right. Because what we're going to do is we're going to combine the efficiency of using a digital camera for the very fast image acquisition display that you want to use for delineating a region of interest at low magnification, but at the same time we want to use the laser scanning confocal to acquire those crisp images at high magnification.
The idea here being that the laser, because the confocal is imaging one point at a time, it takes a while to generate the image because you have to scan the tissue, whereas the camera can generate the image much quicker for you, correct?
That's correct.
Okay.
Yep. And so we're going to perform par-centric calibration for all of those lenses so we know where each one is pointing. And we're going to connect the hardware, so the ZEISS 7 series LSM, for example, to the Stereo Investigator software system. We're going to match each objective to lenses so that we know when you select an objective on your nose piece, which lens should be selected based on which imaging device you're using, the confocal or the laser. Stereo Investigator does that automatically for you. Once it's set up, you don't need to worry about this anymore.
Right, and so it's important to note that this is something that gets done during the setup of your system. The idea being is that once it gets set up, the user no longer has to worry about this. They can just go back and forth between these various settings and not worry about the interaction of the software.
Absolutely. This is a one and done type of situation. It's done when the system is configured for the first time.
Great.
On the ZEISS confocal side, you will be familiar with using Zen software to set your image acquisition settings. In addition to using Zen for that, we will also require that the objectives are calibrated and the parfocal calibration is done. When you're using a separate camera to do your tracing in Stereo Investigator, we'll configure the microscope to automatically select that light path when you want to use that device. And then finally, we'll set up a MBF connect macro in order to connect the LSM microscope to Stereo Investigator.
And the MBF Connect macro will be a key feature in at least one of the steps in the workflow. We'll point that out and show you all how that gets used.
Absolutely.
Great. Thank you very much, Sue. What we'll do next is we'll actually get started demonstrating how this process is performed. To do that, we will begin by working in ZEISS Zen. We will choose the excitation wavelengths. We will optimize our laser settings to improve our image quality. Critically, we were going to want to make sure that our airy disk size is set to the same value for all of our imaging channels. As we mentioned previously, the airy disk size has a direct relationship to the thinness of the optical section that you will be acquiring. So it becomes important to have every laser channel that you're using to image have the same area, or I should say have the same optical section thickness, even if that means setting different area disk sizes. Finally, we will launch the MBF Connect macro in Zen and connect to Stereo Investigator. So let's begin. So let me just show you here that in Zen 2010, under their macro dropdown, we have a function that says MBF Connect. Launching that launches the MBF confocal linked macro, and as you can see, it's now waiting to communicate with Stereo Investigator. Hitting Connect now puts Zen in a position where it's waiting to hear from SI. What we're going to do first is set up our imaging. We'll begin with the light path by setting up our laser excitation channels. Here we're going to image hexed and enhanced GFP. Zen allows you to tailor the bandwidth of your imaging so that you can image various fluorophores, even if they should have some overlap in their spectra. In the acquisition mode, we're going to verify that we are using the objective that we wish, the frame size of our imaging, as well as various other settings. We will have no averaging in this image. We will verify our image size and pixel size. The channel option allows us to verify our laser power and also set up the area units for imaging. Users of this system will want to make sure that the optical section thickness results in the same value across both imaging tracks. This may require setting different area units, as the area unit is defined by a relationship between the wavelength of light being used and the numerical aperture of the objective. Once we have set these parameters up, we are then free to move on to the next step. So after we've set up our imaging parameters in Zen, we're going to launch Stereo Investigator. Something to note here is that there will be a few steps that are different from the conventional workflow. So after Stereo Investigator is launched, we connect the two pieces of software through the MBF Confocal Connect macro. There's a slight pause while this connection is made between the systems, and Stereo Investigator populates all of the hardware lists. Once we've set a reference point, we will hit the live image button. And what you see here now is a live image that's being generated not from the photomultiplier tube, but from the digital camera. As Sue mentioned, this is an important aspect for the ability to quickly find your region of interest and to delineate it. After we've reached the region that we're interested in, we will go to the acquisition menu and launch the Acquire SRS Image Stack workflow. For users who are familiar with us, this process will be familiar with our software. This process will seem very familiar. For those of you who are not familiar with this process, the workflow takes you through the entire process of performing SRS image stack acquisitions. And you can view more about this on one of our webinars that we've posted on our website, and we'll indicate where that is. So in step one, we are indicating some parameters such as the number of sections we will count and the section cut thickness. Now step two is one of the steps that is slightly different. Here we're going to switch lenses from going to a camera to a laser, right, Sue?
We're going to specify what lens we're actually using and the acquisition device that we're using to display the image. And so you'll see in that drop-down menu we had two 40x objectives, one for the camera and one for the laser. And that's all we're pointing out here. We're using the camera right now, so we want to make sure that Stereo Investigator has automatically selected the 40x camera lens.
And once we have the type of image that we want to use to trace, in other words, the digital camera image, then we select the section that we're working on and pick a color for contour and begin tracing. This process would be the same as if you were using a wide field fluorescent microscope or a wide field fluorescent microscope with a structured illumination device. After the tracing of the region of interest is finished, we hit the next step to select the regions that we wish to collect images from. Now, we're going to switch from the digital camera to imaging with the laser to capture the images. And you'll be able to see that the scaling has changed to match what we see in the digital camera.
Right. You can see that the Stereo Investigator is recognized, first of all, that you have a confocal. Second of all, asks if you want to use it. And then when you say yes, it automatically selects the lens scaling that's appropriate for that device.
Right. And this level of integration that we feel makes this a much, much more streamlined process than what you were able to achieve in the past in the context of confocal stereology. Here we're setting up our stereological parameters like the X, Y, C, the X and Y components of our dissector, as well as to indicate the systematic random sampling grid distribution. In step 8, we will be setting our guard zone heights, our probe heights, as well as our mounted thickness height. The mounted thickness height can be obtained empirically. Again, hitting the live camera button, we've already previously selected that we wanted to use the laser from the confocal. And now we will focus up and down, and my favorite process, and I'm sure many of you do this as well, is to focus up above the tissue until you're completely out of focus, and then come down until something is in focus. We'll call this the top of the tissue. We'll then focus down all the way through the tissue, past the bottom, and focus up until we can start to begin to see things be in focus. We will call this the bottom of the tissue, and the difference between the two, the mounted thickness.
Yep, and anybody who's done stereology before knows that what you cut the section at and what it shrinks to by the time you're done with your histological processing are rarely the same.
Correct. So after we have set up our stereological parameters, the next step allows us to save our images and allows us to name both our images and our DAT files.
This is important because it's going to automatically assign a name to each of those image stacks that we're going to acquire.
Step 10 is one of the few places where the workflow differs from a conventional bright field, wide field fluorescence, or structured illumination, in that the top of the section is set in a combination of Stereo Investigator and Zen. So to set the top of the section, we'll navigate in Z through Zen, and when we are ready to set the top, we will hit the resume button on the MBF macro. We will then move the stage to the next location
via Stereo Investigator,
set the top of the tissue section in Zen, and then press the resume button in the MBF confocal link macro to set that top.
Yep, so you're just going to toggle back and forth, but the best part is that Stereo Investigator and Zen know when they're each supposed to play a role. So
Correct.
It's seamless.
And so the data from Zen that you just dictated by setting the top of the tissue gets ported into Stereo Investigator, and a topographical map is generated. We can then save all of the configuration settings that we've generated in Stereo Investigator for a future use. Here, we're ready to begin imaging, and we press the Start Acquire button. And what you can see is if we go back and forth, if we go to Zen, you can see that Zen is now driving the LSM hardware to generate our image stacks.
And it's operating unattended at this point. So what it's going to do is it's going to move to each XY location specified by Stereo Investigator. Stereo Investigator will tell the stage to move to those locations. Zen, when you get to that location, or when the stage gets to that location, will automatically navigate through the section thickness to acquire the desired image stacks that you want, whether it's the entire mounted thickness, just the probe height, or a combination of probe height, guard zone, and images above and below.
Correct. And so what you're seeing now are the two pieces of software, as Sue mentioned, interacting. Stereo Investigator driving the position of the stage in X and Y, and then the ZEISS Zen software driving all of the functionality of the laser scanning microscope.
So this is the point where you could leave the scope to continue to work and acquire these image stacks all by itself. Right. You don't have to be here for this process. And in fact, what we're demonstrating now is relatively short. We only did one section, but Stereo Investigator allows you to specify capture of multiple sections and assign them all to the right locations for you if they're all located on the same physical glass slide. And so you could really set this up to acquire bilaterally 12 to 15 sections if you want.
Right. Once you get your imaging parameters established and the rest of the hardware set up, it's really a quite simple process to get through. So here we see that Zen is finishing up, I believe, the last image stack.
Yep. And once it's done.
Yep. Once it's done, we go back to Stereo Investigator. Stereo Investigator knows that our run is completed. It automatically is saved. And then we hit done.
Okay, so what do you do once you've let your ZEISS confocal run all night, collecting hundreds of image stacks and naming them for you and putting them in a space where you can get them later?
Right.
We're going to take you through the process real briefly of now what. And the option is, or the next thing to do is to count those image stacks. And there's a couple of different ways you can do it. You could use your LSM system, or the computer that is connected to your LSM to do those counts, or you can take them offline to a workstation so that you can use your LSM for other imaging that needs to be done. You would load the data file into Stereo Investigator, and we'd select the optical fractionator workflow because in this case we're going to be counting objects. The data file that we collected with the SRS image stack acquire workflow contains a number of features that are critical in order to be able to analyze the data. We have the stereological parameters that were used during acquisition. We know the location of where each of those image stacks are in X, Y, and Z, as well as across which section they appear in. And we also know the image scaling for those images so that we're going to display them properly. Next, we're going to mark the objects. So the optical fractionator workflow, if you've counted live, you know that there are 12 steps in that workflow. When you run the optical fractionator workflow off of an SRS image stack acquired data file, you only have 5 steps now. And the sole step really that you're going to be spending all your time on is marking the objects. Because we have image stacks, we're able to view the stack in 3D with the counting frame overlaid the image stack. That allows you to double check any questionable features that you may wonder about. Is that on the line? Is it in the guard zone? Is it in the dissector? Now you can load that image stack, see where it intersects with the counting frame, and make an informed decision.
And you could not do this if you were counting it live.
That's correct. That's correct. So that's one advantage of counting with an SRS data file. Finally, like all Stereo Investigator probes, you can view and export the results. Stereo Investigator calculates your estimate for you automatically. It also will calculate the coefficients of errors for those probes and allows you to export them directly to Excel. This streamlines that entire process to make the process of marking your cells to analyzing your data in Excel streamlined and very quick. We provide all of the equations that we use to calculate the data so that you can know where we are coming from. So let's see this in action. So I'm going to switch to Stereo Investigator now. I'm going to place a reference point, and under the Probes menu, I'm now going to select the Optical Fractionator workflow. I'll select Load Subject Data from Existing File and browse to where that location is. I'm going to open the data file. And you can see that this is a data file of the hippocampus. The dentate gyrus is outlined in hot pink here, and the striatum radiatum is outlined here in blue. You can see that we've bounced all the way down to step 4, which is the count objects step. Because we already know where we're going to sample and we've already acquired those image stacks at that location, we're ready to count. So you'll select the acquired stacks and hit start. I'll select an object for marking. And now, when I look, here, let me zoom in a little bit. So let me tell you what we're looking at actually before I get too deep into this. So this is an image series of tissue that was stained with GluR1 for the glutamate receptor and V-glut for vesicular glutamate. Vesicular glutamate is in green and GluR1 is in red. And so this image stack, or these image stacks, were acquired at 100x with a zoom level of 5. And so we're looking at very tiny objects here, obviously.
And as we mentioned before, all of that scaling information is shared between the two pieces of software seamlessly.
Yep. And so now the process of counting is the same as if you were counting something very large like somas. You're going to move down through the image stack using the page up or page down key. And when you enter the dissector, you can see that the counting frame now becomes green and red. And we would mark objects as they appear. For example, I can also show you this in 3D. So we can pop the stack into 3D.
And so this is what you mentioned before. This 3D tool allows you to make decisions about whether or not an object is inside the counting frame or not, depending on this 3D view, and maybe I can see it easier in this way.
Yeah, so it's just an added tool for your arsenal for trying to decide whether or not some of these objects that may be on the edge, whether or not they should be counted.
Right.
So, for example, if you were looking at this synaptic element and you wanted to say, all right, does it come into focus when it touches the exclusion line or not? Let's move through Z and see whether or not that is the case. And so we're out of the dissector right now, and we can see that it is there. So as we move down,
right,
we wouldn't mark that object. So it's just an additional tool to allow you to make these decisions more rapidly and with greater confidence.
Right.
So we would just proceed through the image stack as necessary, marking all of these synaptic elements that meet the criteria to be counted, not just on this stack, but for the remaining stacks on this section and the remaining sections in that animal. Once that's completed, the data is available for analysis and export.
In summary, thin optical sections from confocal microscopes provide the resolution to perform stereology on very small objects, or very small objects that are densely packed, like co-labeled nuclei, synapses, spines, etc. The tight integration between Stereo Investigator and ZEISS Zen is an enabling technology that greatly simplifies rigorous quantification with confocal microscopy. Our automation of image collection and offline analysis offers unparalleled efficiency, and one of our customers has told us that it has made her work 10 times faster, which is exactly what we want to hear.
Absolutely. I mean, think about just the ability to automatically name the successive image stacks across the successive sections that you're going to be analyzing. That's hundreds of sections, saving you the time and the tedium of filling that information out.
And that seems like such a small process, just naming things, but it's such a critical aspect of being able to do this that you don't even think about how tedious it can be sometimes.
And that's the simplest thing that this integration does. We also randomize your locations for you, make it possible for you to move seamlessly between the scaling changes that happen between using your PMT as your detection device versus a camera as your acquisition device. So all of those things work together to make your life a lot easier, a lot more efficient, and a lot more effective.
For more information on confocal-based stereology, we recommend Dr. Daniel Peterson's workshop in Chicago, Practical Workshops in Confocal Microscopy and Stereology. For more information on the course, please visit www.neurorenew.com. For information after the webinar, please email all your questions to info@mbfbioscience.com. If you'd like some information on stereology, you can visit our website, www.stereology.info. And as we mentioned previously, you can view this and other recorded webinars on our website at mbfbioscience.com/webinars.
It'll take us a couple days to get this one up, but once it is, you'll receive an email notification that it is available for viewing. In addition, I would just like to take a moment. I know that this webinar was focused on confocal stereology, but I just want to take a moment to let you know that the integration between MBF Bioscience and ZEISS for this LSM microscope also means that you can use your LSM to acquire virtual tissue images that can be used for tracing neurons or using autoneuron in our Neurolucida product as well.
Correct.
We're going to be at Neuroscience like we are every year, and we encourage you to stop by. Let us know what you are really hoping to do. Let us show you what we can do, and importantly, let us show you how the LSM and Stereo Investigator work together.
Right. We'll have an LSM at our booth, and we'd be more than happy to give you a demonstration.
Yep. So we're going to be right on the main aisle. It'll be very easy to find us. We're at the intersection of the poster aisle and the main aisle.
Visit us at 1437, and also visit ZEISS at booth number 2809.
Yep.
From all of us at MBF Bioscience and ZEISS, we'd like to thank you for joining us today. We hope this has been informative, and we hope to see you at the next webinar.
Thank you. See you in DC.
Bye-bye.